Don't forget to subscribe and ring that bell.
Hey there, guess what day it is? Guess what day it is? It is actually February 14th, Valentine's Day, and I have a treat for you. Ta-da! It's more calculus. It's calculus. Happy Valentine's Day. We are going to continue the 2008 AP Calculus AB practice exam. We are going to be doing free response question number 4. And I don't mean to break y'all's heart, but we don't get a calculator for this problem. So what? Most of the algebra is so much more simpler when we don't get a calculator. It's the setup. Let's begin free response question number 4 right now. Question 4 reads, let f be the function given by f of x equals ln of x times sine of x. The figure above shows the graph of f from 0 to 2 pi. The function g is defined by g of x is the integral from 1 to x, or the integration from 1 to x, of f of t dt for x values between 0 and 2 pi. All right? 4a tells us to find g1 and g prime of 1. All right. Let's come down here, and we notice that, okay, this is g right here. If I want to find g of 1, I'm simply going to place 1 into my x value, okay? There was an x right up here for the upper bound, and we're going to put a 1 there because that's what's going in for x. The lower bound is also 1. That right there tells me what the answer is. It's 0. How come the answer is 0? Anytime the upper bound and the lower bound are the same thing on an integral, the answer is always 0. Okay? So our first one is done. If you want to write it nice and neat, g of 1 is 0. There you go. Now, let's do g prime of 1. Okay? But first, we have g of x. Okay, g of x, again, that's given as the integral from 1 to x of f of t dt. If I am going to take the derivative of g, that means I got to take the derivative of this integral. And the wonderful thing happens when I take the derivative of an integral, they kind of go bye-bye. And the dummy variable, bye-bye, it goes away too. The upper bound goes in, whatever variable or expression that is, goes in for the t. So really, it just equals f of x. Now, the chain rule applies. What do I mean? For example, if this would have been x squared here, I would have put an x squared in for t times the derivative of that, which is 2x. Okay? And that's just a little refresher, but there is no x squared up there. It's just x. Okay? And if I really wanted to, I could say times the derivative of the inside, which is 1. But anything times 1 is itself. I just don't want you to forget about the chain rule. Okay, so now they're asking us for the derivative of g, but this time they want it at 1. So I need to find f of 1. Please, fundamentals, anytime they give us something like this notation, they're really asking for a coordinate. When my x is 1, what's my y? Good thing is I have the graph of f above, so let's just find the coordinate where x is 1. Right here. Bang. Oh, that point. When x is 1, my y is 0. Okay, so I'm going to come back down here. And when x is 1, y is 0. Oh, beautiful. They're both 0. G prime of 1 is 0. And there you go. That was a nice, easy one to start off with. I like it. 4b. On what intervals, if any, is g increasing? Justify your answer. All right. All right. Let's get down to some business here, kids. Let's go pink again because it's Valentine's Day when I'm recording this. Okay, on what intervals is G increasing? All right, so let's think. In order to find out whether G increases or decreases or whatever, I really need to look at the first derivative of G. Okay, I need to look at the slope, right? If it's greater than 0, that means it's increasing. If it's less than 0, that means it's decreasing. And I need to know the critical points where it's equal to 0. That's the critical points. I'm going to call it CP, because that's where it has a tendency to turn between increasing and decreasing function. The issue is, and this is all fine and dandy, what we've said here. I mean, we're correct here. The pink and gray looks so nice. Okay, I need to look at the derivative of G, but the graph above is the graph of F. Well, two things here that I can recall from 4A. And the first one is, they give me the equation for F right here. They give me that equation. That might come in handy. And also, we found out that the derivative of G was F. Okay, so we're going to kind of tie those two together and move forward in 4B. All right? So when I say I want to find out if G prime is either positive or negative or 0, okay, when I say G prime is really f of x. Okay, so that's like saying, well, let's just figure out when f of x, because those are the same things, is either greater than 0, less than 0, or equal to 0. And not only do we have the graph of f here, we know the equation is the ln of x times sine of x. Don't fear. I know we don't have a calculator, so this isn't going to be very difficult algebraically. All right? First of all, let's take a look at our graph. If the graph is the graph of f, and I said this to my pre-calc class today, okay? Anytime we're graphing something, in this case it's f, the y values, okay, the y coordinates are the value of f, all right? So as I look to my little mess over here again, if I want to know when f's are positive, well, that's when f's are positive, that's when y's are positive. Anytime we are above the x-axis. So my y's are positive above the x-axis. That also means my f's are positive. All right? The only time this graph is above the x-axis is from 1 to this point right here. I don't know what it is yet. It looks like it's probably going to be pi, 3.14. But we got to show our work how we got that. Why? Because it says justify your answer. All right. So I guess I could say according to the graph, but mathematically, what if that's 3.4, not, or 3.02? What if it's not 3.14? Pi. Okay, what I'm saying is x is 1. Yep, 1. And we know the graph goes to 2 pi. They told us the interval there. I'm assuming that this is 1 pi. All right? Because I got to give them the interval when my first derivative of G, which is f, is increasing. So when f is positive, okay, so it's between 1, and I'm saying pi here, but I need to verify that somehow, okay? So the second thing about this graph is as follows, all right? My f, which is my y value, is positive anytime above the x-axis. But anytime I touch the x-axis, my f, which is y, is a 0. Okay, so 0 here, 0 here. Again, the critical points, okay? This has to be a critical point, and this has to be a critical point. So I got my first derivative has got to equal 0. Or in this case, f of x equals 0. So look at my equation down below. G prime of x equals f of x. All right? And the function, or the equation for f of x, is ln of x sine of x. Let's set that equal to 0 and solve. I guarantee one of them is going to be 1. The other answer is going to be right there. Okay, and I think it's going to be pi. All right? So we have, this is kind of factored. So what we're going to do is we're going to set each one equal to 0. Ln of x equals 0. Sine of x equals 0. All right. Well, basics when it comes to natural log. You should know that the natural log of e equals 1. And you should know that the natural log of 1 equals 0. That means this x value has to be 1. Okay, so there's our first point. 1, right? Ooh, what color will I do this in? Let's do this nice orange. Big in orange. Right here, that's my x value of 1. That's one of my zeros. Confirmed. Right there. But what about sine of x? All right, well, the sine of x. If you know anything about sine, okay, up, down, that's the graph of sine of x. Okay, it goes up to 1, 0, -1. 0 degrees. This is 180 degrees, or we call pi. This is 2 pi, which is 360, then 90 and 270. So it touches 0 here at 0 degrees. So when x is 0, where else? Right here at pi. Okay, when x is pi. And also right here when x is 2 pi. So look at these three zeros. 0, pi, and 2 pi. Let's go back up to the graph. Oh, this is going to be nice. Watch this. At 0, it's a 0, or undefined. At pi, it's a 0. And then again at 2 pi. There you go. So we just confirmed this is pi. Okay? That is pi. So my interval where g is increasing, okay, where the derivative of g, or f, is positive, is between 1 and pi. Okay, so let's just go ahead and state that. A lot of explanation, okay, and I went into a lot of detail there, where if you understood it, you really didn't have to follow that detail if you knew it. But you're here watching this problem because maybe you don't know it, okay? If you need to, you rewind, you hear it again, you see it, you really put it together. This really is a simple problem if you know your natural logs. Okay, e, the natural log of e is 1, the natural log of 1 is 0. And if you know your sine values, okay? 4c. For x between 0 and 2 pi, find the value of x at which g has an absolute minimum. Justify your answer. Again, in order to find mins and maxes, oh, buddy, in order to find mins and maxes, in this case an absolute min, I got to go to the first derivative. We just did this. The first derivative of g is f of x. All right? The first derivative of g is f of x. All right? And if we want to find a minimum, we want the derivative of g, which is f, which is this graph right here. It's a graph of f. Okay? We want to figure out where it goes negative, because that means downward, hits a 0, then goes positive. So I want my graph of f to go from a negative value to a positive value. All right? Now, let's not forget that this graph, the y is f. That's what it means. Okay? And if we think back on the 4b, we established that this is where x equals 0. This is where x equals 1. This 0 is where x equals pi. And this 0 is where x equals 2 pi. All right? So, ready? Here we go. Keep in mind that y's are negative below the x-axis. That means f is also negative. This is where my f or my y is 0. And anytime we're above the x-axis, my f, which is my y value, is positive. Okay? So look at negative, hits that 0, goes to positive, hits that 0, goes negative, 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 then stops at a 0 again. All right. So keep in mind, if I look to the right side of the screen here, I want to go from negative through my 0 to a positive. All right? So I look at this first 0 right here where I start. All right? And I go lower, negative, 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 negative. I hit a 0, and then I go positive, positive, positive. So here is a min point. Okay, that's one min point at x equals 1. All right? Then as I go through my next 0, I go positive to negative. I don't want that. I want negative to positive. So this is a maximum, not a minimum. So let's continue on our graph. We're going to go negative, 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 and then we're going to stop right here. So you might say to yourself, well, at x equals 1. That's fine and dandy, but we need to find the absolute min. This graph has endpoints. I need to check my endpoints, meaning I start when x is 0 right here, and I automatically start going downward. Okay, so this can't be the lowest point. I hit this minimum where x equals 1. And then I go up. See where this green line is? That means my graph goes up. Okay, I hit this 0 at x equals 1. And then I hit this 0, okay, which is at pi, at x equals pi. And then I go down. But look how long I go down for where it's negative. So I keep on going down, 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 down. I'm thinking right here at the end at 2 pi, that is going to be lower than at x equals 1. Okay? But how do I justify that? How do I justify that? All right. First of all, let's state the obvious. And we're going to use words here instead of math, but we're going to describe the math that goes into it. All right? Let me go into gray. So there are minimums, there are mins at x equals 1 and at x equals 2 pi, which is right here. All right? But the absolute min is at x equals, ready? Let me explain. Let me explain. And I'm going to erase all this stuff right here for a moment. All right? And the explanation is important that you understand this because it might come up at another point. We said this is positive. This is negative. Negative. All right? The area under the curve. All right? The area under the curve gives me my value. If I take the area under this curve right here, okay, that's a small area, okay? That's this line going down like this. It's a small number. If I take this area and add it to that, right? So let's go over this here. This is a negative number if I integrate that area, correct? This is a positive number here. But it seems that when I go to the area under the curve at the end, this is going to be a much larger negative number, okay? Which means this is going to also be negative, but it's going to be a bigger negative, okay, than this one is, all right? So that means I'm going to go further down on this one. So this is where my absolute minimum is going to be. And I'm going to word it just like that. They're not asking me to come up with the actual minimum value. They just want me to say, well, if I'm going to pick 2 pi as my absolute minimum, justify it. Okay. Let's justify it. Is that x equals 2 pi? How come? Because the area under the curve between pi, oh, I should do this, and 2 pi is a, I mean, do we want to say a bigger negative or more negative or smaller? I would say is a bigger negative value than the area under the curve. Extend that from 0 to 1. And that's exactly how to word it. Now, anytime I word things like this and use explanations, and I've had this happen before, people comment, it's like, well, you can word it like this. Yeah, there are a million different ways you can word this. Someone might say, like, well, I might not give that full credit. Whatever, then write it the way you give it full credit. I like that. That explains I know where I got my solution from. I pointed out the solution, and I justified it with my explanation based on the graph they gave me and the math that's involved in that graph. Okay? I've had people write an explanation on another video I did where I had something similar to this, and they knocked it out of the park. But it was like a paragraph and a half. I know this might seem like a lot of writing, but someone wrote this long thing, and I was like, man, that is very detailed. That is full credit. Very good. And there are a million different ways where you can write something very detailed to full credit. Just be specific. When you write things down, make sure you be specific. The area under the curve is bigger here than there. Bigger where? Bigger between pi and 2 pi than it is between 0 and 1. Okay, let's look at our graph. Bigger between pi and 2 pi than it is between 0 and 1. Okay, be specific. That's the only thing I can tell you. That's what makes a full credit problem different than a partial credit problem, being specific. 4D. For x values between 0 and 2 pi, is there a value for x at which the graph of g is tangent to the x-axis? Explain why or why not. Well, before I do the math here, and by the way, this problem is pretty much done already in some of our previous work. I'll explain in a moment. But you need to understand what tangent to the x-axis means before I just start showing you the math. All right? So, forget about the graph of f for a second. Let me just draw something else here. We've done plenty of problems where, okay, if I come up like this, come up like this, come up like this, like that, like whatever. Let's say I have a graph here. If I want something tangent to this point right here, that means it has to have the same slope. It has to touch that point. The coordinate has to be there. You need to have the coordinate right there, and it needs to be parallel. The slope has to be the same. Okay? The slope, whatever the slope is at this point, the slope of this line has to be the same. Okay? Let's pick another one right here. I'll do this one in green. If I pick a point right here, okay, not only does this point have to, this is where it has to touch the line, but it has to have the same slope as this point. Okay? Keep that in mind. Now, the problem says, is there a value of x at which the graph of g is tangent to the x-axis? If it is tangent to the x-axis, that means the coordinate has to be on the x-axis. Okay? That means it's got to be somewhere like this, one of these points. Okay? Any of these points. Guess what? All these points have one thing in common. The y value is 0. Okay? So if it's on the x-axis, my y value has to be 0. And if it's parallel, if it has the same slope as the x-axis, the slope, which I'll call m, also has to be 0. Like, let's take a look. I drew this graph intentionally like this. See this point right here? Okay? Not only is the coordinate on the x-axis, but if I draw the line, that slope has to be the same as the x-axis, which is 0. Okay? So that's what you need to know to solve this problem. So in terms of g, two things need to happen. I need to find an x value where my y is 0. Okay? Because remember, this is a coordinate. And then I also need to find where the derivative or slope is also 0. Okay? Let's go to 4a. We've already done this work. G of 1 is 0. Guess what that means? That's a coordinate when x is 1. Oh, and let's look over here. What about the derivative or the slope at 1? That's also 0. We've done this work already. If you botched up 4a, I feel bad for you. I don't think you can do 4b. So guess what? At x equals 1, explain Doesn't tell me how to show my math work. Since g of 1 equals 0 and g prime of 1 is 0. Done and done. For 4C, I went on a little rant at the end saying be specific. Okay? Don't just say since y is 0 and slope is specific. The y at what value of x? The one they're asking you to solve for. The slope at what value of x? Okay? Be specific. Easy. Very easy problem to end. Happy Valentine's Day. We're done. Like the video. Give me a little comment if you need to. And follow me. Follow my channel because that's how you get notifications when I put up new videos like free response question number 5. Coming soon to a theater near you. Visca, the teacher. Calculus. Fear everywhere. Number 5. I'll see you then.
Don't forget to subscribe and ring that bell.